Welcome to this VMworld session about Kubernetes networking with NSX-T deep dive. I am Ali Al-Idris. I'm Network and Security Solution Architect in the EMEA Technology Practice Team. And here with me is Yves Fauza, who is a Technical Product Manager in the Network and Security Business Unit. And we both work for VMware. So this session may contain some features or products for the future, and they are subject to change. So we will start today's session with NSX-T overview, and after that, we will follow it with Kubernetes overview. Both overviews are very high level, just the information we need to understand the integration between NSX-T and Kubernetes. After that, I would say the main part of the session, which is the integration piece itself. And we will provide a technical deep dive regarding the integration between NSX-T and Kubernetes. And finally, we will conclude the session with a demo that Yves will run. And finally, we will have some time for your questions. So please leave your questions to the end. So let me start with NSX-T overview. I would say high-level overview. So with NSX, we had the vision of having NSX everywhere. And NSX-T is a special flavor of NSX that is fulfilling that vision. It's a flavor that is decoupled from vSphere and vCenter, so it can support non-vSphere environments, such as other hypervisors, KVM, for example, and to support public cloud. And more importantly for us in this session is the support for cloud-native apps. The support for cloud-native apps by the ability to extend the network and security policy beyond the virtual machine up to the container level. So NSX is an abstraction layer. It's a network and security virtualization that works as an abstraction layer on top of any physical IP network. And it consists of multiple layers. The first layer will be the data plane. And the data plane consists of what we call the transport nodes. The transport nodes are nothing but the host, the hypervisors themselves. And that could be E6i or KVM today. So we have those transport nodes, okay? And we have what we call the edge node. And the edge node is responsible to run some advanced layer 3 features and some stateful services, such as NAT. We have another type of nodes, which could be the bridging node. And their job is to bridge the physical VLANs to the logical space, okay? And the data plane is distributed and high available by nature. On top of the data plane, we have the control plane. And the control plane consists of 3 controllers. Those controllers' job is to build the logic that is needed for forwarding, such as all the tables needed, such as MAC tables and so on. So we can make the forwarding decisions in the data plane. Now, the control plane is highly available, and those 3 are there for high availability reasons, redundancy reasons, and even for scalability reasons, because they share the load between each other. On top of that control plane, we have the management plane. And the management plane consists of the NSX manager. This is where you place your configuration. This is where the API is. This is where the GUI is. Okay? So you can configure the whole network and security within NSX. Now, this API in the NSX manager could be consumed in multiple ways. In a cloud consumption model, if you have a cloud management system, you can use this API using Ansible, for example. And this is where we deal with the integration with Kubernetes. So Kubernetes will talk to the API of NSX manager. So from management plane and control plane perspective, we place our configuration in the NSX manager And we can use the GUI or the API for that, right? This is where our configuration is persisted. From that management plane, the configuration will be pushed to the control plane, to what we call the centralized control plane, the CCP. We will build all the logic, the tables are needed, and we will push them in what we call the local control plane. This local control plane exists in all the transport nodes. Okay? So any forwarding decision will always happen locally in any transport node. We will not need to send any packet to the control plane. The control plane is totally out of the data path. So in case on failures in the control plane or the management plane, the data plane will not be affected. From data plane architecture perspective, I'll start here by explaining the routing piece, and then I will go to the switching piece. From routing perspective, in NSX-T, we have two-tier layers of routing. We call them the tier 0 and the tier 1. The tier 0, you can look at it as the provider router, is the router that will do the peering, the route peering with the physical infrastructure. And the tier 1 router, you can look at it as the tenant router. Okay? Now, both the tier 0 and the tier 1 in NSX-T are distributed. So they exist in all the transport nodes, including the edge nodes, which is different from NSX for vSphere architecture, I would say. Okay? So both tier 0 and tier 1 are distributed in all the transport nodes. They exist everywhere. The tier 1 typically will act as the default gateway for the virtual machines in that tenant, and the tier 0 will be used to do the routing between the tenants and for the north-south traffic to take the traffic outside of the virtual environment to the physical infrastructure. Now, as I mentioned, those are distributed, exist in the transport node and the edge nodes. The edge nodes is together, you can have multiple edge nodes, and each edge node could be a VM form factor or a bare metal form factor. Okay, it depends on the performance requirements in your environment. So those edge nodes together, they will form the edge cluster, which you can look at it as one big router, okay, one big logical router, the edge cluster. And we use DPDK to enhance the performance in those nodes, okay? Now, the traffic will only go to the edge nodes for north-south routing as an exit point to leave the virtualized space, or to apply stateful services, such as NAT, where we need to have a centralized node to apply that. Right? From switching perspective, to make sure that NSX is abstracted from the physical infrastructure, right, which is a main concept in NSX, we use overlays. Okay? And that overlay is between all the transport nodes. Okay? The choice of an encapsulation in NSX-T is Genève, which is a next generation encapsulation. It's a standard that came after VXLAN, and it has some advantages over VXLAN, such as bigger fields for the metadata, so we can have better visibility in the fabric, we can have more information within that header, and probably some future, I would say, functions. And every switch, by the way, will consist of every logical switch will consist of a specific Genève tunnel. So this is just a high-level overview of NSX-T. There are other sessions within VMworld who will explain that. There is an introduction session, and there is some detailed sessions on NSX-T. They are just after this session, I believe. And here is the code for that session. And there is a hands-on lab here in the VMworld for NSX-T specifically. So you can go ahead and go through it. So let me move now to Kubernetes overview. And again, this is a very high-level overview just so we can understand the integration piece. Otherwise, we will need probably 2 hours to explain Kubernetes. So Kubernetes is an open source system to automate the deployment, the operation, and the scaling of containers on top of a cluster of hosts. Okay? It started internally by Google IT in a project called Borg. This is what Google used in their internal IT, and they donated it to the CNCF, where it started as an open source project, and today Kubernetes, I would say, one of the top open source project, if not the most popular open source project in the open source community. Kubernetes cluster consists of what we call the masters and the nodes. You can look at the masters at the management, right? As a management plane, I would say. And and the nodes are the places where you place your actual containers. Okay? The master, and you can have multiple of those, 2, 3, depends on the scalability and the high availability requirements in your cluster, right? Will consist of multiple components. The API server is the component where you place your configuration using the Kubernetes CLI or using API calls, right? But the API server is not only for external communication in the Kubernetes cluster. It's even used for the internal communication to the nodes and other components within the Kubernetes cluster. More importantly, I would say, is the etcd, which is a distributed key value store in your Kubernetes cluster. You can look at it as the brain, the memory, the database in your Kubernetes cluster. Okay? The other component in the master, right? We have the scheduler, and the scheduler job is to place the container in the right node based on available resources or specific criteria. There is a native scheduler on Kubernetes, and you can even hook a third-party scheduler for that, right? For more advanced decision-making, I would say, in your Kubernetes cluster. Then the controller manager, the controller manager job is to make sure that the pods, and I will explain pods later, you can look at them as container for now, to make sure that the pods, the deployments, and the cluster is in the desired state. Okay? And then we have the dashboard, which is nothing but a GUI, an optional GUI, I would say. From the node side, we have the kubelet, and the kubelet job, and it exists in every node. Okay? The kubelet job is to watch the API server for what we call the pod specs, right? So it can deploy the pods based on the configuration done in the master, right? It will deploy those pods and containers using the container runtime, which most probably it's Docker, but it could be other options such as Rocket, okay? We have the kube proxy, which mainly responsible to do Kubernetes services such as east-west load balancing using IP tables, which is NAT. Okay? So I mentioned the word pod multiple times, which is a very important concept in Kubernetes, right? A pod in Kubernetes is a group of containers, okay? So you can see here like a group of Docker containers, for example. And those containers share the same IP address, the same TCP IP stack, okay? And the same storage volume. Typically, a pod is a group of containers that represent a single service or function, okay? So they are very tightly coupled together. In many situations, a pod is a single container, right? But in some situations, it could be multiple containers. For example, here, we have an Nginx server, and it needs a logging server. And they need, obviously, to share the same storage volume, right? So they are going to be in a single pod. The TCP IP stack will be owned by what we call a POS container, and its job to own the IP address and to do the volume, to access the volume, the storage volume. Okay? Another important concept in Kubernetes is the namespace. And the namespace, we can look at it as a tenant. Okay? You can look at it as a folder or as a tenant. It started as a folder, but I would say it's matured now with time to be more of a tenant. And it will provide a multi-tenancy concept within Kubernetes. And this is a very important concept because we use it heavily in our integration with NSX. So the namespace is a way to provide resource quotas, role-based access control, specific resources for specific namespace. And you can have the capabilities of name overlapping. Okay, so you can have a Redis master pod within the full namespace, and you can have Redis master with the exact name, but in the bar namespace, similar to what we do with folders, right? The way load balancing natively happens in Kubernetes, there are two ways, the east-west load balancing and the north-south load balancing. For the east-west load balancing, we use what we call Kubernetes service. And Kubernetes service is a way to group multiple pods together and provide a cluster IP, which is a virtual IP. That cluster IP will exist in all the nodes. So if a pod wants to communicate to a group of pods in a load balanced way, it will talk to that cluster IP, which exists in all the nodes, and then the Kubernetes node will use IP tables to reach the desired pod. Okay. For the north-south load balancing is a bit different. So we use what we call Kubernetes ingress, which is a way to map a URL or a host name to a Kubernetes service. And typically from the Kubernetes ingress, we will reach what we call an ingress controller. For example, it could be Nginx ingress controller, HA proxy, or it could be even a third-party load balancer such as F5. Okay. And from that, we will load balance to the pods. Okay. So native networking in Kubernetes is done in a way where every node is a subnet by itself. You can look at every node as a router. Okay. We have the management IP per node. And then we have the subnet for the pods themselves. And every node will have a different subnet. For example, here we have 10.24.1, and we have here 10.24.2 subnet. Okay? So every node is a separate subnet. And then we have the management IP for those nodes. Now to reach those pods from the physical infrastructure, we will need to configure static routes because there's no way to do dynamic routing with those nodes. Okay, so we will need to configure a static route per node. Okay, now as you see, this is a basic networking, and the other, I would say, gap here is the fact that there is no networking multi-tenancy. Subnets are associated with the physical infrastructure. Subnets are associated with a physical node. They're not associated with namespaces and tenants, right? So you can't tell actually this pod by looking at the IP address it belongs to which tenant, for example. Okay? And we can have direct routing here to access those pods because every pod in the cluster have its own IP address. Okay, and we can route to it. You can simply route to it. Now, to avoid the fact that we need to configure the physical infrastructure, most deployment use overlays, right? And a very common overlay, there are a lot of technologies, but I would say a common one is Flannel, which is an open source product that use overlays between the nodes to abstract from the physical infrastructure, to avoid the need to configure the physical infrastructure with static routes per node. Okay? And they use VXLAN overlays by installing an agent in every single node. Okay? Now, obviously, yes, that would help from physical infrastructure perspective, But it could complicate the north-south access for those pods, the external access, the user access to those pods, because now we will need to use NATing and hide the IP addresses for the pods just to access them using the node ports. Okay? The other thing, even though this will help in the physical infrastructure configuration, it's still a subnet per node. Okay? And all the pods in a specific node will use a single IP for north-south traffic. And they will differentiate them using a port number. So now let me move to the main part of the presentation, which is the integration piece. All right? So it was just a high level about NSX-T and Kubernetes, and now I want to explain the integration piece, which is why we are all here in today's session. So I will start explaining the end result, how it will look like after the integration, right? And then after that, I will explain the components and what are the components and the architecture for the integration itself. Now, in this diagram you see here, we have Kubernetes masters and Kubernetes nodes. And in our architecture, those are nothing but virtual machines. Could be on top of ESXi, could be on top of KVM. Okay? So those Kubernetes master and Kubernetes nodes, and we have already NSX-T integrated with Kubernetes here. We have the tier 0 router already paired with the physical infrastructure using BGP, for example. Okay? And we created some IP blocks that we will use for the IP address management, for the IPAM. Okay? Because NSX will take care of the pods IPAM in our architecture. Okay? So once you go to your Kubernetes master and you create a namespace, so kubectl create namespace foo, NSX-T will automatically react by creating a tier 1 router, attaching it to the tier 0 router, creating a logical switch, assigning a subnet from the IP block that we already configured, so it will take the first available subnet in that block. Okay? And and we'll configure some NAT boundaries here. That's the default behavior. I'll explain the other behavior later. Okay? And it will configure some NAT boundaries. Now, it's very important to note that this subnet is not associated with a physical node anymore. It's a logical subnet. It's an NSX logical switch that exists everywhere. Okay? It belongs to a tenant. It doesn't belong to a node anymore. So a node could have multiple subnets, and a subnet could exist in multiple nodes. This is totally abstracted from the physical infrastructure. So we have this subnet, and then when we create another namespace, for example here, bar, NSX will automatically react, will create another T1 router, it will name it bar, attach it to the T0 router, create a logical switch, and it will it will take the subnet, the second available subnet, in the IP block that we configured. Okay? When we create a pod, for example here, Nginx foo, in the foo namespace, NSX will attach that pod in the right logical switch that belongs to that namespace. You create another one, it will do the same. You create another pod in the bar namespace, then it will attach it obviously to the bar logical switch that belongs to the bar namespace. In case this subnet is totally consumed, NSX will automatically react by creating another logical switch. It will take the next available subnet and it will attach it to the tier 1 router that belongs to this namespace. Okay? Now I explained the architecture that we use with NAT. You can have the option when you create the namespace from the Kubernetes side to have direct routing. Okay? So when you create a namespace in Kubernetes, you can add an annotation saying no not true. And by doing that, NSX, when it creates the infrastructure needed for that namespace, will not configure NATing. That's one. And the second thing, it will assign a subnet from the direct routing IP block, because obviously we will need different IP addresses now that are routed in our infrastructure. Okay? And you can do that when you create the namespace from the Kubernetes side. Okay? So in this example, this is a routed subnet that will have direct routing, so you can access the pod with a its unique IP address. No NATing is involved here. So you can have the choice when you create the namespace to have it NAT, and then all the pods in that namespace will share a single IP if you don't want to utilize your IP addresses, right? Or you can have direct routing with those pods. Now, the important part to note, in both architectures, subnets are not associated with physical nodes anymore. They are associated with tenants. So even in the NATed way, you still can tell which tenant it belonged to using that IP address. Okay? So I explained the connectivity part to the pods. Now let me move to the security part and how can we secure these pods. And this is a very critical piece when it comes to NSX, which is the microsegmentation part and the distributed firewalling. Now there are two ways we can secure pods in a Kubernetes environment using NSX. The first way is what we call the predefined label-based rules. And in this example, right, we already configured the security groups and the security policies from the NSX side. We only do the placement in the Kubernetes side. Okay? So we already configured them. We applied the right policies for those security groups and security policies. What we do in the Kubernetes side, we use Kubernetes labels. So you can label, for example, this pod here with sec group equal web, and it will be placed in the web security group. If you label this with security group DB, it will be placed in the database security group. And the policy will be applied based on what you already configured from the NSX side, what you already applied to this security group. Okay? Now again, it's important to notice that the placement and the security groups architecture, so the security zones, I would say, is abstracted not only from the physical architecture, but even from the logical architecture, from the networking architecture. So you can have multiple pods in different tenants belong to the same security group. Or you can subdivide a specific tenant to multiple security groups. It's purely based on labels. So you can label whatever pod in whatever namespace, and you can group them together from security architecture perspective. Another point is we can even microsegment that security group by protecting those pods that belong to the same security group from each other. So we can do microsegmentation to pods, containers, right? The same way we do it to virtual machines today with NSX. Okay? Regardless if they are on the same node, the same namespace, the same subnet, it doesn't matter. Okay? So the other way of doing that, probably if some of you already involved in some Kubernetes project, and you know there is something called Kubernetes network policy that was released in Kubernetes 1.7, okay? And Kubernetes network policy, when you create a pod, you can decide what ports to open with that specific pod, okay? So we can do that. So you can create a Kubernetes networking policy, specify the ports you want to open, and it's again based on Kubernetes labels in the Kubernetes networking policy. But now in this architecture, the security groups and the security policy are not created in the NSX side. So everything is created from the Kubernetes side. So you create a networking policy from the Kubernetes side, and based on that, NSX will configure the security groups and policies dynamically. Okay? Now, it's important to note that today, Kubernetes networking policy is an ingress policy only, and it can only apply to Kubernetes objects because it uses Kubernetes labels even from the source side. So we cannot configure a generic subnet as a source. You cannot configure users to pod, for example. Right? You can configure pods to pod. And there are some limitations when it comes to configuring the networking policy when protecting pods in different namespaces from each other, I would say. But I would say it will mature with time as Kubernetes mature in the coming releases. Okay? So when you apply the networking policy in the Kubernetes side, NSX will dynamically create the security groups and apply the security policy based on what you already configured in the Kubernetes networking policy. So this is a dynamic creation of the groups and the policies. Okay? So just to summarize the security part and the microsegmentation, there are two ways to secure pods in a Kubernetes environment using NSX. You can use the predefined security groups and policies and just do the placement from the Kubernetes side, or create the whole policy from the Kubernetes using Kubernetes networking policy. And I would say it depends on the operational model. Who should create the policy, right, in every environment? This is one thing. And the other thing, you can use the networking policy as long as you understand the capabilities and the limitations of that, right? So let me move into the load balancing piece. So I explained the connectivity part, the security part, and now I will move to the load balancing. And again, I will explain the east-west load balancing and the north-south load balancing, how we do it with NSX in a Kubernetes environment. So we have a component called NSX Kube Proxy. It's our own component that exists as a daemon. And Kubernetes, a daemon is a pod that exists in all the nodes, okay? So it exists in all the nodes, and it will take care of the east-west load balancing. So we have distributed load balancing using OVS load balancing, the OVS that exists inside the Kubernetes node, okay? Which is, I would say, higher performance than the native Kubernetes IP tables. For the north-south load balancing, when we create a Kubernetes ingress, NSX will automatically create the NATing rules that is needed to reach the ingress controller. And then we can use, for example, Nginx ingress controller to load balance to the pods for north-south load balancing. And we just did testing with F5 for the north-south load balancing, and we will publish the results soon using F5 load balancer, a virtual F5 load balancer for the north-south load balancing with NSX. So I will go a bit deep dive now of the components that
Go ahead.
No. Okay, it's back. I'll try not to walk, or I don't know.
I don't think it's you.
So, yeah, so from the integration piece. So from the integration part, we have a centralized component and a distributed component. So the centralized component is what we call the NSX container plugin, the NCP, okay? The NCP is a centralized component that sits between the NSX Manager API and the Kubernetes API. It will watch the configuration in the API, in the Kubernetes master, and based on that, it will push those configurations to the NSX Manager, okay? It is built, it's available in a container image, so it could be deployed as a pod anywhere in your Kubernetes cluster, as long as it has connectivity to both the Kubernetes master and the NSX Manager, right? The NCP is built in a modular way. So we have today the Kubernetes adapter, so we have the integration with Kubernetes, but we have the possibilities to add another adapters for the integration with other container management systems, right, such as Pivotal, Cloud Foundry, and PKS, and so on. Now, this is an example of how the workflow when we create a namespace. So when we create a namespace in the Kubernetes side, first the NCP will watch the Kubernetes master, the API in the Kubernetes master. So when a user creates a namespace, then the Kubernetes API server will notify the NCP of the change. And then the NCP will create the tier 1 router, attach it to the tier 0 router, create the IP subnet, and so on, all the flows that we saw before. Now, if we go a bit deeper dive, this is the distributed component. This is what exists in the nodes themselves, right? The Kubernetes nodes. So every Kubernetes node, which is, again, it's a VM for us here, yeah, will have what we call the NSX-CNI plugin. So the way we differentiate between the pods within a single node is using locally significant VLAN tags. So the CNI plugin, the NSX-CNI plugin, will tag the traffic coming from those pods, and then it will the NCP will map that VLAN tag to what we call a container interface, CIF. That container interface will exist in the hypervisor virtual switch. So the traffic will always go to the hypervisor virtual switch. And then we will apply the policy in the CIF. And by doing that, we can have all the advantages, all the features we can have for virtual machines for containers. And more than that, this model will help us scale better, because we don't need to control every virtual switch and inside every single Kubernetes node. We only need to control the hypervisor part of it, okay? Another point to note, and I think I need to move a bit faster, is the management interface. So the management interface is separate from the interface that we use for the pod's traffic, which is different than the native networking Kubernetes, because the management interface was used for the pod access, not in our architecture. So we do separate those two. So this is where the management interface for the node, and this is another logical switch, NSX logical switch, that is used for the pod's traffic. This one has an IP address in the VM level, in the VEF. This one doesn't have an IP address in the VEF level, because we will access directly the pod's IP addresses inside that node. Okay? So this is my last slide before the demo. It's the operation and visibility side, which is, I would say, probably the most critical piece in the whole thing. So if you used NSX before, you know the visibility features such as trace flow. And this is a snapshot of when we can have a trace flow between two pods. And we can see all the logical components between those two pods. Which logical switch, which logical firewall, which logical router they go through. If there is a firewall policy blocking the traffic between those two pods, we will point to that policy and we can go to it and change that, for example, right? We can have trace flow, port mirroring to a specific pod, port connection tool to see the overlay and the physical infrastructure in between, spoof guard, syslog, port counters, and IP fix. And we can do all of those per pod. So all the visibility and the operational tools we have for virtual machines, now we have them for pods, okay? And we can have that in a unified environment, right? It doesn't have to be an isolated environment. And now, it's time for a demo,
my turn.
The mic is yours.
So I dare to do a live demo. So what you see here is my environment. I have a vSphere environment with some nested hypervisors, and on there I have 3 Kubernetes nodes, 1 master and 2 nodes. And as Ali said, here on that node you can see, or not because it's pretty small, that I have 2 network adapters. One is connected to a regular port group, that's my management network. And down here this is connected to an NSX-T logical switch. This is where we multiplex the traffic on. I also have a database VM here, just to, you will see it later in the demo, just to show that we can mix VM workloads with Kubernetes workloads here. So let's go over here. First thing I want to show you is the namespace creation. So we'll look at Kubernetes, what namespaces are in the system right now, and those are the default ones that come when you install Kubernetes. And once the NCP starts up, the first thing it will do is it will create a logical topology for those namespaces. So here we see Kubernetes cluster 1, default, kube public, and kube system. The integration we did is completely multi-tenant, but also multi-cluster. So you can have any number of Kubernetes clusters using the same NSX-T environment. And we differentiate them by a prefix. That's why we have Kubernetes CL1 here. So what I will do now is I will create a new namespace without any annotations. And as Ali said, this will create the logical topology with NAT. So here's my new logical switch. I was just created. And if I look at the ports, I have one port, which is my logical router port. If I look at the logical router for it, my tier 1 router, it is here. And if we look at the router ports, you see that we gave it an IP address 10.40.41 here. That IP address comes from the NSX IP address management, which is here. And we have a number of blocks, and one of them is this block that serves the 10.400/14 block. And it assigns subnets out of that block. And here we just assigned this last one here to that namespace. So the whole management of IP addresses is done in NSX also. And different clusters can either use the same blocks or they can use different blocks depending on how we tag the resources. Now going back to the routing, here on our central tier 0 router, we can see that we have NAT entries. And those NAT entries are specific to the namespaces. So the last entry here is the namespace that we just created. And it got mapped to a specific IP here, hard to see, to a specific IP, so we can match by source IP what the traffic is, where the traffic is coming from. Sorry for the, yeah. So that's the IP address that we use here, and this also comes from an IP pool that I created in NSX. And the projector is gone again. Okay, it is back. And gone again. So let me create a no NAT namespace. So here we see we have an annotation no SNAT true, and I will create the namespace by using this YAML spec. So here I say create me the namespace, but create it from the spec. Now what happens in the background, I'll refresh the routers. I won't show you the logical switch because it's just the same thing that we just saw. But here the logical router got a IP address out of a different block, right? And on the tier 0 router, if I go to the services and NAT, then obviously you see nothing changed. There is no additional NAT entry for the 172.20 IP address network because it's a no NAT namespace. Okay, so let's deploy a little application here. So yeah, the namespace we already saw. I will create a new namespace for that application. I'll call it Yelp app. And then I'll configure Kubernetes to use that new namespace for everything that I do going forward. And here I'll just point Kubernetes to a file on a GitHub repo. And this is my own GitHub repo here. And this is the specification of my app. And I have a web front end here. And that web front end here has a special label, which is sec group web tier. I also have an application tier, which has a sec group app tier. Okay, and then I have a couple of services here, and at the end, I expose my application on that host name with the pass / and gone again. Okay, so what happened here is I told Kubernetes to create it. It went and created all those necessary objects. And the first one here, the first container is already running. The second one is running now. And if we look again with some more information, we also see the sec group label here and the app tier label here. Okay? And we can look at the ingress and we'll see, okay, this is my host name. So before I go into starting the application, let's go to the switching part here again. And let's refresh. And then we go into the Yelp app namespace. And you see those are my ports. And down here, you see I copied all the labels I got from Kubernetes into port tags. So I get all the metadata from Kubernetes and I apply that to objects in NSX so that I can match with those objects. What I didn't show you at the beginning is my database VM part here. That's my database VM that is also patched into NSX. So here's my VM name RedisDB. So NSX also knows all the VM names of the attached VMs. Now if you look at the inventory here, there are groups. Those are dynamic groups. The first one is for my DB server and it matches simply on the VM name. So here the membership criteria is if the virtual machine name contains RedisDB, then I want that logical port, gone again, that logical port to be a member of it. Here you go. So the logical, that's annoying. The logical port is mapped into that group. If I look at app servers, the membership criteria is the tag equals app tier and the scope equals sec group. So that's the labels we just saw in my application definition. And indeed, if I look at the logical ports, they are matched here. Okay? So that's how we match those Kubernetes objects into things that NSX understands. So let's call the application here. And it's a simple voting app. And so you can vote for your favorite restaurants here. And the backend, which is my Redis database, now stores all those votes. Okay, so everything's fine, everything's cool and working. Let's break it. So I'll go to the firewall here. And you see the firewall rules we applied are based on those groups that I just showed you. So here we have the web tier group. And we drop any traffic between the web tier group members because we don't expect web servers to talk to each other. We have the web tier talking to the app tier. We have the app tier talking to the DB server. And we're always using those groups and specific ports. So let me change this rule here that allows the app tier to database traffic. Obviously that broke our application, hopefully. And as you see, voting is dead and my Redis database access is gone, just as I expected because I just dropped it. So how would I go about troubleshooting this? And troubleshooting the projector, maybe? So I don't have a tool to troubleshoot the projector, but I have a tool to troubleshoot what happens inside of NSX. So here I'm selecting a logical port in TraceFlow. Here we go. And that logical port can be my Kubernetes pod. And here I'm using my app server pod or my app server logical port as the source. And then I'm using the RedisDB, where is it? RedisDB as the destination. Okay? I go into advanced because I don't want to send ICMP traffic. I want to send specific TCP traffic from some ephemeral port. And on the database port 63, that counted up, 79, okay? Then I send trace, and what happens in the background is now that NSX goes the whole path, sends the traffic, and then analyzes what happens on each of those hops. And the results are placed as metadata into those Geneve headers, so that at every hop we can actually analyze what the result is. And that's not the projector that is causing a problem here. Here we go. So here I can see the complete path. I can click on all those elements here and see what elements I have in the path. Now in this case here it's pretty easy. We are dropping the traffic already when it enters NSX because we have a firewall rule blocking it, and it's the firewall rule 1085 that is blocking it. Let's double check if it's really 1085. Indeed, that's the one I changed. So let's change it back. And then we'll refresh the application, and hopefully I can vote for my favorite restaurant again. Here we go. And that was for the demo. Sorry for the glitches with the projector. I know it was not nice, but I hope I was able to still show you the value of NSX even with a broken projector. Here we go. Ali?
All right. So team, as we showed, the NSX-T will provide a lot of values in the Kubernetes environment from networking and security perspective. It will have enterprise class networking with direct routing, NAT, multi-tenancy, advanced security with microsegmentation and security per pod, and enhanced operations with the visibility tools that Yves just showed one of them actually. It will provide a unified VM to pod networking, so it's not only for the cloud-native apps, it's a standard networking layer for virtual machines, traditional apps, and for cloud-native apps in a unified architecture for Kubernetes and OpenShift environment, actually. It will provide pods microsegmentation, the way we showed it, where you can have a security policy per pod, and full networking visibility with counters, with trace flow, IPFix, and so on. And I would say more importantly, you have VMware covering your back in case of problem with enterprise support. So there is a lab for NSX-T and Kubernetes integration. Please go ahead and try it yourself. It's a very interesting lab. It's available here in VMware and VMworld, and it will be available in hands-on labs, in VMware hands-on lab publicly.
So one thing I'd like to add to this HOL, it's based on an alpha version that we had, so we had to publish it pretty early. So what you'll see is alpha. You won't see the things like the no-net namespaces, but if you come to your VMware account team and say you would like to try a version that is like the newest one, we can give you access to a pod to test it out, to a vPod actually, not to a Kubernetes pod.
And actually, I advise you to go and look at this blog written by Yves regarding the integration with, I would say, some more details. And yeah, try it in the labs, go to VMware documentation. Please fill out your survey in the app. We really appreciate your feedback. And when you fill it, please try not to skip any questions because they are assumed zeros. And thank you very much for your listening, and we have time for questions.
Do we have a mic? Yeah. If you could wait for the mic so that the recording has your question.
Thanks. It's basically about architecture of the Kubernetes project you just showed to us. It's pretty similar to what vSphere Integrated Containers is currently doing, like all the networking, the separation of the different networks for the control of the nodes, and like you said, the kubelet agent, which is pretty much the theta agent of VIC. So the question would be, are there any plans for merging those two projects together? Because the main difference I'm seeing here is that you can use the Kubernetes API and the Kubernetes syntax, but pretty much the architecture is the same.
So, I mean, what we showed you is the integration of NSX-T with either do-it-yourself Kubernetes distributions or selected Kubernetes distributions of partners we work together. PKS, which was announced, is our own distribution of Kubernetes, which will include the NSX-T integration. But we're also working with other players in the market, like IBM or Red Hat, with their Kubernetes distributions. So the goal of NSX is to be able to work in a multi-cloud, multi-hypervisor, and also multi-container distributions environment, right? Now, at some point, will there be a merging of having VIC to work with Kubernetes? We are not the ones that could answer that. That's a different group of people that are defining and working on VIC and on the VIC roadmap. So you should go to one of their sessions and ask it there.
Okay, thank you.
So I'm coming from an NSX-V and VM point of view. When the distributed firewall is applied at the VM NIC level, where is the distributed firewall? Is that at the container interface level? And does that manifest as a NIC each time on each node, or is that sort of one NIC for all the nodes?
So if you look at the NSX connectivity, let's say, you have one VIF interface which goes to the VM. So we see the VM interface. And then those container interfaces, they are technically speaking sub-VIF interfaces. So there is also a way to see which VIF has child interfaces, and those are the container interfaces. Now those virtual interfaces all live on the hypervisor layer. Up on the node VM itself, you will see those interfaces in Open vSwitch, and then mapped to the IP namespace, not the Kubernetes namespace, the IP namespace of the Linux node.
What the hypervisors are you looking at integrating? At the moment you've got KVM and ESXi. Is Hyper-V on there or anything else?
Technically we could integrate with Hyper-V. Right now we are looking into the future of our hypervisor support. The current release doesn't support Hyper-V. The current release supports KVM on either Ubuntu or Red Hat Enterprise Linux. And it supports vSphere 6.0 and 6.5 and 6.5 U1.
And with IPAM management, at the moment NSX-T provides its own IPAM function in there. Is there any views to integrate it into things like Infoblocks, where, well, for example, ourselves as a corporate, we use Infoblocks for all our IPAM management. We wouldn't want something like NSX-T to, well, we wouldn't want to federate that out to NSX-T.
We currently don't have any committed plans to have this IPAM hooked up to Infoblocks or some external system. It should be pretty easy to populate what is in NSX-T by an external IPAM. So to build some logic that takes a block out of Infoblocks and puts it in. So it is doable, but right now we don't have any immediate plans to build it into either the NCP or NSX-T itself to be able to hook into an external IPAM. But it's just logical that we will support it at some point in the future, just not right now.
Sorry, and last question. The NCP and the way the NCP speaks to the Kubernetes master, that's full REST. It's not doing something like a folder scan or something on Kubernetes master.
So that's the greatness of Kubernetes. Kubernetes supports those watching capabilities. Actually, it's etcd that supports that. It's an HTTP REST interface, certificate authorization and authentication. And once you register to watch certain resources, you get the callback from the Kubernetes API. Thanks. So there is no polling. That's the greatness of Kubernetes. Other integrations need some polling, but the Kubernetes integration has watching.
That's configured from the NCD. That configures the Kubernetes.
Yeah, so etcd itself provides the streaming API and the watching capabilities, and the Kubernetes API is basically providing a sanity layer in front of it, an authentication authorization layer, and then forwards the requests or forwards the changes to whoever watches.
That's a push. So the NCD actually tells the master who to push to.
And what we are building, the NCP does exactly that. It watches for namespaces, it watches for paths, it watches for network policies, etc. As soon as it sees something change or something newly was created, it takes action and does something.
Okay, thank you.
There's one question down there. I guess that will be the last one.
What if we would have Kubernetes on bare metal?
Yeah.
Any plans to support that?
So NSX-T as a platform is going to take care of public cloud use cases where we support NSX-T in AWS and those clouds. It takes care of the multi-hypervisor use cases with vSphere and KVM support. And longer term, we are also looking into bare metal integration. But it's not in any committed release right now, but we are definitely looking into it. And so if you would come by after the session and tell us where you need it and how you want it to look like, then we can take it into our considerations. Okay, thank you.
Okay, thank you.